Hello, everyone. Welcome to CosmosDB conference. My name is Karthik Purushothaman. I've been in tech industry for last 20 plus years. I've played multiple roles in multiple domains, mostly on the technology side. I have reasonably good experience in developing enterprise-grade applications. And I'm currently working with Stream. It's a data integration and streaming platform company. Today's talk is going to be on change data capture and how we are going to implement change data capture using Cosmos Change Feed. And this is going to be the agenda for next 30 minutes. I'll first start off with what exactly is change data capture, and then we'll go over the CDC requirements for implementing a streaming ETL architecture. I'll be using the abbreviation CDC right through the session, and ETL stands for extract, transform, and load. And next we'll see, basically we'll deep dive into Cosmos Change Feed and how to implement a CDC using Cosmos Change Feed. Then finally, we'll be looking at a full-fledged ETL demo, which is implemented using Cosmos Change Feed. Okay, so what exactly is change data capture? Basically, it's a process of observing all the changes that are happening on a database and to take action based on the change data to apply it on multiple targets. Maybe I could explain this with an use case to make it more clear. Assuming you have a write-heavy database, we call it as a source, and there is a whole lot of DML operations that are happening on the database. And there is a need to replicate this database to another database, which is read heavy, and all the indexes and other things are configured or optimized for read heavy usage. And also you need to replicate the data to a cache. So this is the high level use case. So basically all three data sources should be in sync and it should be synced in real time. That's the use case. So there are a couple of approaches through which we could implement this. One is we could do dual write or multiple writes, which is like the source application, which is updating the database, should also perform the same write operation on these two targets. But doing a dual write or multiple write is always error prone and can lead into data consistency issues. And the other way to achieve or to keep the data sources in sync is using triggers. Basically, you could set up triggers for the source database, and on trigger is fired, you could actually update the target databases. But even with the triggers, if the volume of changes that are happening on the database is pretty huge, it is not so reliable. So that's where CDC comes into play. So before we see what exactly CDC is, let's take a look at how the database is kind of implemented internally. In the sense, like for most of the database vendors, they keep track of the changes that are happening in the database through something called as logs. And each vendor has their own convention to name the logs. Say, for instance, RDBMS databases typically call them as a transaction log. And say, for instance, Mongo call it as an operation log. So any changes that happens in the database is a kind of tracked in this log. Technically speaking, like if you have the complete history of the log, you could actually recreate the entire database from the logs alone. So CDC actually relies on this log to capture the changes that are happening on real time on the database, and then convert that into a stream of events and push it into a message broker, something like Azure Event Hub or Kafka or a lightweight 0MQ. From the message bus, the targets can subscribe to that and they can pull in the events and then apply it to the respective data store. So this is the high level use case of what CDC solves. But the use case is not just limited to this. With CDC, you could actually do a whole lot of other use cases, something like real-time anomaly detection, like as and when the changes are streamed into the change stream, you could perform some analytics on top of this and then do some anomaly detection. Or if you want to create a materialized view out of the original database, then you could make use of CDC to create materialized view. So basically, the use cases are unlimited with the CDC mechanism. So next thing is like we'll try to understand what are the typical CDC requirements that are required to implement a streaming ETL architecture. So traditionally, ETL used to be a batch processing in the sense like we extract data from data source, do some transformation, and load it to a target. And this kind of kicks in on a timely basis, like every 1 hour or end of the day or end of the week. Typically, it's more of a batch processing. With CDC in place, you could actually do a real-time ETL or a streaming ETL for which you need to capture the changes happening on the database in real time. That's one of the fundamental requirement. And there might be cases where you have historical data present in the database and you want to do an initial snapshot migration to the targets followed by doing a CDC. That's another requirement. And you could also do checkpointing on the CDC, and then basically you could stop the CDC pipeline and then try to resume at some point in later based on the saved checkpoint. So that's another requirement. And obviously, there shouldn't be any data loss. And with respect to event delivery guarantee, the events that are happening on the source database should be delivered in the same order to the target. And uh, we should try to achieve the exactly one semantic. If that is not possible, we should be able to implement at least one semantic. Basically, exactly one semantic is like delivering the event to the target exactly once. And for at least once, as the name suggests, each event would be delivered at least once to the target, which means the target can expect duplicates for several events. So with these requirements, we'll see how Cosmos change feed helps in achieving these requirements. So let's take a look at what exactly is a change feed in Cosmos DB. So it's nothing but a persistent record of changes that are happening on the container, and they also preserve the order in which they occur. Basically, Azure Cosmos provides a nice SDK, Java SDK version 4 for SQL API. So using this SDK, we could actually query the changes that are happening on the container in real time and consume that in our client application. So there are a couple of models through which we could fetch the changes from the container. One is push model. As the name suggests, the change feed processor library provided by the SDK kind of constantly pushes the changes that are happening on the container to the client application. And on the client application, we should have handlers to receive the events or the changes and then process them. This is kind of convenient for most of the basic use cases, but if you want to have much finer control for advanced use cases like say for instance, if you want to control the pace at which you are receiving the changes from the container, or if you want to read changes from a specific partition key or a specific logical partition, then pull model is the way to go. So as the name suggests, like the client application will be constantly pulling changes from the container, and then after receiving the changes, it kind of processes that. Since it's up to the client to receive the changes from the container, it can actually control the pace at which it is receiving. This might come in handy in scenarios where you have a pretty slow targets and you need to handle back pressure on the source side. So the rest of the session is going to be based on the pull model. So in order to query the change feed, a couple of configuration has to be passed. First thing is like we need to tell from where to start the change feed. Again, there are two type of configuration in that. Like you could start based on some point in time, which could be like you could start from the beginning or current point in time or some any desired point in time. So this is like if you say I want to get the change feed from beginning, what this means is after the container is created, any changes that happened in the container will be retrieved via the change feed. And the other way to decide on where to start is using the continuation token. So continuation token is kind of a bookmark that is provided by change feed, which could be persisted and used it to resume the change feed at some point later in time. So that's another way you could query the change feed. And with respect to what to query as part of the change feed, you could actually specify which logical partition you want to query. That is kind of acts as a filter to your change feed query. Or if you want to query the full changes that are happening on the container, that is also possible. So let's spend a minute on trying to understand what exactly is a continuation token before we move further. So as I said, like continuation token is kind of a bookmark or checkpoint which is provided by the change feed. So it's kind of something provided for every page of changes from the change feed. Typically, when you query the change feed from Cosmos container, it is returned as a collection of page, and each page can contain multiple changed item. And the continuation token is kind of issued one per page, and the format is a binary data, which is totally internal to Microsoft. Just in case if you are curious to take a look at like how a continuation token looks like, here is a sample decoded continuation token, but don't try to interpret this continuation token and try to consume the information in this, because this is something bound to change. Okay, with all this information, let's see how to implement a CDC flow. Here is a simple pseudocode on how a CDC could be implemented using change feed. So the first thing we need to do is like we need to pick a starting point in time for the change feed. As I was saying before, it could be beginning or based on current time, or it could be some user-defined time. So once you identify where to start the change feed, you pass that to the change feed query, and the results will be returned as collection of pages. And each page contains one or more changed items. So what you do is once you get the collection of page, for each page, you push all the items in the pages to an external stream. The stream could be Azure Event Hub or Kafka or ZeroMQ, and you save the last continuation token of that query. So once you're done with this, you query the change feed again with the last saved continuation token. And once you get the results, you just do the processing just like before. And every time you're done with the current set of pages, you save the last continuation token and use that for the next query iteration. And you continue to do this in a loop so that you are constantly pulling changes from the container and processing them. So this is the high-level CDC flow. We'll take a look at the demo, and then we'll also take a look at the code on how this is implemented. So couple of points to be noted before we move to the demo. So, the change feed actually guarantees the order of changes within a logical partition. It doesn't guarantee the order to be intact across a logical partition. Say, for instance, if you have configured city as your partition key, and if you have two distinct values like Chennai and Mumbai, so all the changes that are happening in Chennai would be returned in the same order as it happened on the container. Similarly for Mumbai, but the order across the partition is something not guaranteed. Since ordering is kind of guaranteed within a logical partition, we could actually query the logical partition changes in parallel so that we could do much faster processing. So these are things that we need to keep in mind. With all this information, I have put together a streaming ETL application, which kind of solves the original problem where I started. So you have a kind of a write-heavy database, which is Cosmos DB SQL API, and you have a replica database, which is Cosmos Mongo, and you have Azure Cache for Redis. So the funda is like any updates that is happening in the Cosmos DB SQL API database should be propagated instantly to both the cache and the MongoDB. And in the process, there could be some transformation happening, and then the data would be finally updated on the targets. So I call this as a source and these two as targets. And as I could see, we leverage the change feed APIs from Cosmos in order to read the changes. And the changes are read using a reader app. So internally, if you look at, there are multiple threads that are spinned off, one thread pertaining to one logical partition value. Say if you have two distinct logical partition values, something like Chennai and Mumbai, you'll have two threads running in this reader app, fetching the changes simultaneously and pushing the changes as an event to Azure Event Hub. So inside Azure Event Hub, again, you could have more than one partition. So basically, we shouldn't get mixed up with the number of threads here, with the number of partitions here. The number of partitions inside Azure Event Hub is not directly proportional to number of threads here. This could be anything from 1 to 32. So that's the limit of Azure Event Hub. So anytime when you publish an event from the reader app, what we do is, in order to retain the order, what we do is like we publish the event key along with the event. Say, for instance, the thread one is publishing all Chennai related events. So it sends the Chennai as the event key. And the moment Azure Event Hub receives event along with the key, what it does is it applies a hash on the key and then decides which partition that particular event has to go. Say, for instance, the first event is routed to partition 1, basically for a Chennai event. Then all subsequent events pertaining to Chennai partition will be routed to partition 1. Same goes for the other logical partitions as well. So on the target side, we have a couple of apps. One is to read the events from the event hub and update the cache. So here, if you see, we have same number of threads corresponding to the number of partitions in the Azure Event Hub. So if I have like only two partition configured in the Event Hub, then you'll have two threads running on the target application, which will independently fetch the events from the respective partition and then update the cache. The same goes for another writer app, which reads from the event hub and then updates the CosmosDB API. So this is the high-level flow for this streaming ETL application. Let's take a quick look at the demo. So before we go to the demo, I could quickly show you the setup in the Azure portal. So you have the Cosmos SQL API, which is the source database. And you have a couple of targets. One is the MongoDB and the other one is the Redis cache. And Azure Event Hub, which actually connects the source to the targets. And let's take a quick look at the content of the source database. So the source container is a kind of a flight database with the schedule as the container. And you have items in the schedule container. So the JSON structure looks something like this. You have the ID, start city, final city, flight code, departure arrival. Yeah, the basic flight database related information. And if you look at the target, currently nothing is there in the target because we haven't started any CDC. Now, yeah, this is the Azure Event Hub where two consumer groups are configured. One is for updating the cache and the other one is to update the MongoDB. Now, let me go to the demo. So I have totally 4 applications. The first application is the one that reads the data or reads the changes from the container. I call it as a source CDC application. And you have a couple of applications for the target. One which actually updates the MongoDB and the other one updates the cache. Basically, this application waits for changes happening on the container, and these two application actually waits for events from the Azure Event Hub. And I have a fourth application, which is just a utility application to push data into the container to demonstrate the CDC capability. So Now, since the source database already contains 10 items with the IDs ranging from 1 to 10, what I'll do is I'll start the targets applications. Just wait for this application to be up and running and start listening for events from the event hub. So the expectation is the moment I start the source application is actually started with the point in time as a beginning. So what this means is it will try to fetch all the existing items from the container and then propagate that to the respective targets. So let's go ahead and fire up the source. Okay. As you could see, the moment the source CDC app started, it actually retrieved all the existing items from the container because I used beginning as the point in time. And all those 10 items are propagated as event to the respective targets, one to MongoDB and other one to cache. As I was saying, if you look at, if you pay attention to this ordering, the inserts actually happened in the order of like Mumbai, Chennai, Mumbai, Chennai. As you could see, the IDs are sequential, ID 1 to 10. But if you look at the ordering in the change feed, uh, the ordering within logical partition is honored. For instance, the ordering within Chennai, if you look at 2, 4, 6, 8, and 10, that is honored. And similarly for Mumbai, the ordering of events is honored. And on the target side, you have two threads which are reading from the event hub and then parallelly updating the target. The same goes for the cache target as well. So now, after reading the initial snapshot from the source container, the source CDC application is waiting for new additional changes that are happening in the container. So let me start this utility application and try to insert a few more items into the source container and see whether those events are getting propagated to the target. So I'm just inserting. So every time when I hit enter in the utility console, it's going to insert one new item to the container. As you could see, it inserted a new item with ID 11 and the city as Mumbai. So that is again cascaded to the targets. So let me insert multiple items. And as you could see, the items the changes are captured in real time and then propagated to the target. I mean, from the target side, if you want to see what is the content in the cache, so this is give the key and then try to query the value from the cache. Basically, it returns the actual JSON. As you could see, it returns the item corresponding to the city Mumbai and have the information saved in the target. So now I go back to the source, which is the Cosmos SQL container, and let me do an update to one of the items. Maybe I'll change the status from scheduled to started, and then update the item. So I expect the item with ID 1 to be read by the source CDC. As you could see, changes are instantaneously read and they are propagated to the target. Now let me try to check the value in the cache. Enter 1. As you can see, the status is now updated as departed on the cache as well. Now, yeah, so with this, as you could see, the CDC application is capturing the changes in real time and cascading them to the target. So let's try to simulate a crash scenario and see how this checkpointing and recovery works. So what I'm doing is assuming for some reason the source app goes down unexpectedly, and in the meantime there are a bunch of inserts are happening in the container, and by the time the source app comes back, there are a whole lot of changes that happen to the container. So the expectation is the source app should read from the point where it left, and it should read all the new changes alone and then propagate that to the target. So let me, so as you could see, the last maximum ID that was published was 26. Let me stop the source app. Okay, Now what I do is I insert a bunch of items into the container. So starting from 27, I inserted till 40. So as you could see, like both the targets are not receiving any events because the source is stopped completely. And now if I start the source, it should start from the point where it left, which is, I believe, ID 27. Let's see if I start the source app again. Okay, so as you could see, it started receiving from ID 27. Again, the ordering within the logical partition is honored. So that's the reason you see out of order across partition. But the point is like it resumed from the place where it stopped, and then it cascaded the new changes to the target, and the target got updated with that. So yeah, let's take a quick look at the target Mongo collection to see if it has the container. So as you could see, it has all the items populated here. And if you look at the event hub, you should see spike in activity as we were pushing the events into the event hub. So that's what I have for the demo. Let's take a quick look at the code. I don't want to go through the entire code. I just want to show the critical piece which does the CDC. So basically, on the source app, which is constantly looking for changes from the container, I have a class called a change feed poller, which takes a Cosmos client and a qualifier which contains which database and which container to query, and a checkpoint store, which is used to save the continuation token and use it back during the recovery, and a publisher instance to publish the events to the external message broker. So here, if you look at the pseudocode, whatever I explained in the slide, so here is the corresponding code for that. So you invoke this query change feed API on the container instance with a request option. So the request option is typically could be one of these three. Basically, if you have a last continuation token saved, you could use that continuation token and resume from that point in time. Just in case if you don't have the last continuation token, what you do is if you have a timestamp provided by the user, then you make use of the timestamp and then you prepare the request option. Or you could actually start from the beginning of the container. So in addition to deciding on where to start, we could also configure what exactly to query. So either you want to query the complete range of changes, or you want to query only the changes happening in a particular logical partition. In this case, this particular setting is configured where we specify the partition key value as either Chennai or Mumbai in this case. So once we prepare the request option, we pass it to the query change feed, and in turn it returns a collection of pages. So for each page, there is a continuation token associated with it. And what we do is we save the continuation token from each page, and we publish the content of the page to the message broker. So the content of the page is nothing but a collection of changed items, which you could retrieve using this get results API. And then you keep publishing that to the external stream. As you could see, like in addition to saving the continuation token locally, we are also pushing the continuation token into a checkpoint store, which is a persistent store. The funda is like as you keep retrieving the changes from the container, for some reason, if the application goes down in the middle, we could make use of the last saved continuation token and resume from there. So that's how the crash and recovery, whatever I demonstrated, works. It works based on the last saved continuation token, and the query change feed actually resumes from that continuation token. Okay, so other things, yeah, that's pretty much what I wanted to show in the code. Rest of the code are related to the event hub, and on the target side, receiving the events from the event hub and updating the cache. And there is another module or other application which actually updates the target MongoDB. So let's go back to the slides. So as I could see, we managed to build full end-to-end ETL pipeline with Cosmos change feed and Azure Event Hub and other services. So let's take a moment to see how this entire architecture scores against reliability and scalability. As we were seeing, like if for some reason if the reader app goes down and if it comes back, it is able to resume from the point where it left. So there's no zero. I mean, there is no data loss at all. And the same goes with Azure Event Hub, because Azure Event Hub was internally built for handling all the reliability issues. So there won't be any data loss or reliability issues with respect to Azure Event Hub. Similarly, on the target side, for the applications which are reading from the Azure Event Hub, just in case if they crash for some reason and if they want to resume from the point where they left, they could make use of the checkpointing mechanism that is available in Azure Event Hub. So just like how we explicitly implemented checkpointing logic for the reader app, on the writer side, we could actually leverage the Event Hub checkpointing infra to resume from the place where we left. So that's about the reliability aspect. And with respect to scalability, as you could see, each of this layer can be scaled out independently. Like if you want to spin off multiple instances of reader app, one per logical partition, we could do that. And obviously, Azure Event Hub could be scaled out by having more partitions. And on the writer side, again, you could have multiple instances of writer app, one per partition in the Azure Event Hub. So we could actually build a enterprise grade ETL pipeline with all of these services put together. So we saw the demo, we saw the code. Yeah, there are few limitations that developers should be aware of with respect to SDK version 4 for SQL API. Any field update that happens on the source side, we don't get information on which field got updated. Rather, the full item is always retrieved from the change field. So that is one limitation. And there is no information on what type of operation that was performed on the container, whether it was an insert or update or delete. That information is not available as on today. And the delete is something not captured as part of change field. So Microsoft recommends to use soft delete in order to capture the delete. So these are like kind of limitation as on today, but the SDK and the change feed mechanism is constantly evolving. So some of these limitation might be addressed in upcoming releases. So to sum up, change feed is kind of a underrated but powerful mechanism to non-invasively capture the changes happening on the Cosmos container. And as we saw, like a change feed could be used to build a reliable streaming ETL pipeline, which could be used to address unlimited real-time use cases. And here are some of the reference material, a couple of books, and of course, a documentation from Microsoft. And the last link is our company blog. This particular link contains a wealth of information about change data capture, streaming, and data integration, because that's what we do day in and day out. So feel free to check out the blog to find a lot of information about these topics. And thank you for participating in this session. Just in case if you have any questions, feel free to contact me via LinkedIn or via mail. And source code for the demo is available in GitHub. Thank you again.